Welcome back. I'm Muggsy, and today I'm going to explain naming ionic compounds. Before I explain how to name an ionic compound, you should know just how to make ionic compounds from two separate ions. You should also know something about ions themselves, and finally, polyatomic ions would be a good thing to know about. I have videos on all of these things. You should check them out before you watch this one. I will also be talking about covalent compounds. You don't need to know about them. So if you haven't got to that point in your chemistry class, don't worry about it. It's not going to affect anything. You don't need to go look it up to get the most out of this video. Okay, so let's talk about naming ionic compounds. At this point, you should know that if you have a chlorine and a sodium, that you can find the charges of these two elements by looking in the periodic table. You can see that chlorine's in column 17 with the rest of the halogens, so it has a -1 charge. And sodium's in column 1 with the alkali earth metals, it has a +1 charge. Sodium's a metal and chlorine's a nonmetal, so they're going to form an ionic bond. So they're going to come together to form NaCl. We put the Na first, and then we put the Cl second. We do this because Na is the cation. It has a positive charge. Cations go first. And then the chlorine is the anion. It has a negative charge, and anions always go last. We would call this sodium. We just say exactly what the first, what the cation is. And then for the anion, if it's a single element, we just start with the first 1 or 2 syllables. In this case, it's 1 syllable, chlor. And then we add "ide" to the end instead of its normal suffix. So instead of chlorine, we say chloride. So it's just that easy. Before I talk about the structure of ionic compounds, I'm going to talk about the structure of covalent compounds. Covalent compounds, such as water, for example. So here's my oxygen, surrounded by 6 electrons. It can form 2 bonds to hydrogen. And so let's do that now. And so we have 2 hydrogens stuck on an oxygen. If we were to kind of draw this out, it might look something like this. We might have a big old oxygen with 2 little hydrogens stuck on it. Put little H's there. And so if I had a bunch of water molecules, I would have a bunch of these individual 1 O's and 2 H's. But that's not the same with ionic compounds. With an ionic compound, like let's say sodium chloride, table salt, I've got my Na, and it's stuck together with a Cl. And notice that it's not stuck together with a bond that I drew out as a line, like I did with my covalent compound. Again, it's okay if you don't know about covalent compounds yet. What sticks it together are these charges. Positives and negatives attract, because as you know from childhood magnetism, opposite charges attract and like charges repel. Okay, so if I had a bunch of salt, it wouldn't actually look like a bunch of individual NaCl's. Like if I had a bunch of water, it would look like a bunch of O's with H's stuck on it. But with my ionic compounds, it's different. Because remember, if I had a bunch of sodiums and a bunch of chlorines, they would all be stuck together based on charge. So I would have if I had another nearby chlorine, it would be attracted to that sodium, right? Not that chlorine. Let's add on another chlorine. It would be attracted to the sodium, not the chlorines. Add on another one. It would be attracted to the sodium. Okay, now let's add some sodiums. What will my sodium be attracted to? Well, a good place to put my sodium would be right here, because it would be attracted to both these chlorines, and it wouldn't want to be by this other sodium, because opposite charges attract, like charges repel. So if I had more sodiums, they would want to be by the chlorines and not by the other sodiums. Okay, let's add even more sodium now. Okay, I'm just going to go crazy and add all the sodium I can and all the chlorine I can. We'll see what happens, right? And you'll notice what I've actually formed here is called a crystal lattice. And this is the structure of most ionic compounds. Now, it won't be perfectly square like this because sodium and chlorine have a 1-to-1 ratio, whereas a different ionic compound, like let's say magnesium chloride, has a 1-to-2 ratio. So it's going to have a slightly different structure. But ionic compounds form these big crystal lattices, a big grid of charges that are attracting and repelling each other until they form this nice crystalline structure. And if you've ever seen table salt, you know that it's a bunch of little tiny crystals. And sometimes, if you've seen a big chunk of salt, it's a big crystal. So sodium and chloride and chlorine come together into this big crystal lattice of NaCl. So when we say that it's NaCl, sodium chloride, we're not talking about a bunch of individual NaCl's together. We're talking about a big grid of NaCl. But the chemical formula is still important here because what it's telling us is we have 1 sodium and 1 chlorine. And if we look at our crystal structure here and we actually count up all of these, it might be, I'm not sure, let's say it's 12 to 12. That's going to simplify to 1 to 1. So this, the chemical formula of ionic compounds is really just a simplified version of this crystal lattice structure. And again, because there's only one way of putting NaCl together, we don't need to say di, tri, tetra, anything like that. We can just say sodium chloride. Even if it's 2 aluminums and 3 oxygens, we don't need to say dialuminum trioxide. We just say aluminum oxide. Okay, you'll see here I have a bunch more examples of ionic compounds, and we'll just go through and name these. The first one, 3 calciums and 2 nitrogens. Again, we just start with the cation, calcium. Then we've got nitrogen. We just take the first 1 or 2 syllables, nitr, and then instead of rogen, we do ide, calcium nitride. Easy. Next, we've got magnesium. That's our cation, so we just write it out. Now we've got the polyatomic ion hydroxide. Again, if you don't know about polyatomic ions, you should probably check that out. With polyatomic ions, you don't need to change the ending at all. You just write them down exactly as they are. So we would call this magnesium hydroxide. If you don't have your polyatomic ions memorized yet, now might be a good time to kind of go over them. Here we have the cation potassium, so we're just going to write that out, potassium. And then phosphate is our polyatomic ion. So again, with the polyatomic ions, you don't need to do anything to them, you just write them out as they are. And we call this compound potassium phosphate. Here we have iron 2, and then this isn't another Roman numeral, this is the element iodine. So we start by just writing out iron. Then, because I include the oxidation state, you actually need to include it in your name, because they do matter, they can be different. And then we call this iodide. Iron 2 iodide. Now there is a little caveat here, and that is, in the olden days, we used to use different terms for these oxidation states. I'll get to that in just a moment. Let's do this bottom one first. Here we've got iron 3 is our cation, so we just write that down. And then our anion is iodine, so we do, instead of doing iodine, we do iodide. So the only difference between these two is, we'll call this iron 2 iodide. Notice how I say the 2 out loud. And this one I would call iron 3 iodide. Now, here's that caveat I talked about. In the olden days, they used special words for iron 2 and iron 3. They would call this ferrous for the smaller one. Ferrous iodide, and they would call this ferric iodide. Basically, the smaller oxidation state gets an us ending, and we use fer because If you look in the periodic table, the symbol for iron is Fe. Ferro is kind of like the Latin term for iron. And then we use the ic ending for this bigger one. Now, if you're my student, don't pay any attention to what I just said. And in fact, most chemistry teachers nowadays, we don't use this convention at all, ferrous and ferric, because it's kind of complicated, it's hard to remember. In my opinion, it's a bit antiquated and old-fashioned. It's much better to just say iron 2 iodide. And I'm really telling you exactly what that oxidation state is, iron 2. Now, if you're in the know, you should, and I say ferrous iodide, you know that that's the same as iron 2. Same thing if I said ferric iodide, you know that's iron 3 iodide. But to me and to many chemistry teachers, it's easier to just do away with these old-fashioned ways of naming them and just use the Roman numeral oxidation states. Okay, I'll give you one more example, and then I think you'll be really solid on naming these ionic compounds. You'll see here I've got the chemical formula of ammonium bonded with sulfur. There's 2 ammoniums to every 1 sulfur, because ammonium, as hopefully you have memorized by now, has a +1 charge. It's the only polyatomic cation, and sulfur has a -2 charge, so you're going to need 2 ammoniums for every 1 sulfur. Okay, so what do you do when you have a polyatomic cation as the first thing in your ionic compound? Well, you just do like you do with every other cation. You don't have to change anything at all. So if this were sodium, we could just write sodium. If this were magnesium, we could just write magnesium. And if it's ammonium, we can just write ammonium. And then for our sulfur, we just do what we always do. We take the sulf, and then instead of we put ide on. We call this ammonium sulfide. And it's just that easy. I think naming ionic compounds is one of the easiest skills in chemistry class. And what's so cool about it is you don't need to bother with all these things that you might need to later on when you learn about covalent compounds, like di, tri, and the naming conventions for naming organic compounds and all that. You really just need the cation, the anion. You don't even include any numbers, right? We don't need to call this ammonium 2 sulfide or diammonium sulfide. We just call it ammonium sulfide, because ammonium's the cation and sulfur is the anion. It's beautifully simple. Okay, you really have everything you need to know to go ahead and practice this skill. I hope it all made sense. If not, you can watch it again, I guess. I'll see you next time. Thanks a lot.